Hello, and welcome to our presentation on causal variational autoencoders. This presentation is part of our course curriculum DS7290 at Northeastern University. To introduce you the topic, I would like to tell a story. Once upon a time, in a galaxy far, far away, maybe not that far, in a classroom nearby, there is a student, Susan, who's going through a dilemma. She has an old photograph, but she's not smiling enough in it, and she wonders if she could intervene and make herself smile. Suddenly, there is a loud crash. Who appears? It is the causal man. And causal man says that I just know exactly the way how to do it. So Susan asks, will you do it for me? No, but I will enable you to build a solution yourself. I will teach you the fundamentals. I'm going to teach you causal variational autoencoders. So this project has three objectives. The first objective is looking at variational autoencoders from the eyes of causality. The second objective is to establish a causal structure between the images that we have and the ground truth independent factors, which we will talk more about in the upcoming slides. And the third is to utilize the causal prowess to study the effects of intervention and counterfactuals on the data set that we have.
Coming to the data set for our project, we have a D-sprites dataset, which is a dataset of 2D shapes, which are procedurally generated from 6 ground truth independent latent factors, which are as follows: color, shape, scale, orientation, position X and position Y. And we can also see the corresponding factors that they can take in, like for example, 6 values which are linearly spaced in a range of 0.5 to 1. In our dataset, we have roughly 700,000 images. Coming to the main question, so what are autoencoders and how are they different from the variational autoencoders? So an autoencoder accepts input and compresses it and then recreates an original input. So this is an unsupervised learning technique because all you need is the original data without any labels of known correct results. But this cannot be used for our generation as the encoded feature space does not capture the underlying distribution of our data, which in turn does not enable us to create meaningful images. For example, changing values even a little in the feature space might render the image intangible and unrecognizable. How are variational autoencoders better and how are they different from the autoencoders? So a variational autoencoder assumes that the source data has some sort of underlying probability distribution, such as, for example, a Gaussian distribution, and then attempts to find the parameters of the distribution. The model learns the mu's and sigmas and ensures a continuity in the feature space. Thus, tweaking the same can lead to sensible images. For example, in the slide, we can see that a person without glasses, and learning from the image, we try to decode it, and the person can be seen with glasses. So we are able to create a meaningful image out of it. So we tried to train our model, and on reconstruction, we found some very promising result, which can be seen as follows. Here we are also trying to change all the 6 latent factors to see the reconstructions accordingly. So why do we need causality and what role does it play? So basically, learning in disentanglement aims at finding a low dimensional representation consisting of multiple explanatory and generative factors of the observational data. So how does this play a role in the real world scenario? So in real scenarios, features are not necessarily independent. There can be underlying causal structures and dependencies, which we can capture by understanding our variational autoencoder as a structural causal model.
So here we explain the causal representation of variational autoencoders. Causal layers transform independent exogenous factors into causal endogenous ones that correspond to causally related concepts in data. The input signal passes through an encoder to obtain independent exogenous factors and then a causal layer to generate causal representation, which is taken by the decoder to reconstruct the original input. And that's where a causal DAC comes into action. The first question that might strike your mind is how. So once the VA is trained, we create the structural causal model, which allows us to define a relationship between the images and ground truth variables such as position, shape, scale, etc., to obtain the latent factors. This in turn enables us to make inferences about images based on intervened structural causal models and to observe the effect of changing independent factors on the images. So here we'll shed some light on what are exogenous variables and endogenous variables. So exogenous variables are a factor in a causal model whose value is independent from the states of other variables in the system. On the contrary, endogenous variables are a factor in a causal model whose value is determined by the states of other variables in the system. So here we explain the DAG through this graph. We only sample exogenous variable values nx, ny, and nz from any Gaussian probability distribution. In our structural causal model, z, x, and y are deterministically driven by the values of nx, ny, and nz. The main idea is to shunt all randomness to exogenous variables only. X comprises of our images in tensor form, Y comprises of the 6 ground truth factors, Z is the latent variable obtained from mu and sigma as an output of the encoder. Conditioning on structural causal model. In order to check the causal inference of conditioning is working on SCM, an image was randomly generated and reconstructed by passing it through a conditioned model. So as we can see here that the reconstruction done on these images are pretty good, explaining that the conditioning done on RSCM was up to mark. So moving ahead, we explain that what intervention is and how is it important in the process of causal modeling. The term intervention refers to an intentional change in the system you are modeling. Any model that can predict the outcome of an intervention that is unseen in the training data qualifies as a causal model. Hence, we have performed various interventions and shown that the model which we have built can qualify as a causal model. Here are two examples I would like to walk you through. As we change shape to heart and scale and position to given values, our model does generate a required image. Similarly, in the second case on intervening the shape to square with other given values, as shown, it generates the required image. Counterfactual. The main difference of interventions and counterfactuals is that whereas in interventions you are asking what will happen on average if you perform an action, in counterfactuals you are asking what would have happened had you taken a different course of action in a specific situation, given that you have information about what actually happened. So let me walk you through 3 steps of counterfactuals. First, we perform abduction, where we update the probability of unobserved factors. Followed by action, where we perform an action in the SCM model, for example, pyro.do. Thereafter, we perform prediction, where we predict y in the modified model. And that's where we see the promising result of our structural causal models.
Now, what is the desired future state that we can hope for? Let's get back our protagonist, Susan, and her interaction with the causal man. The causal man asks, how will this understanding add value to your life? So which Susan says, with understanding of causal variational autoencoders, I'll be able to build solutions to change features in an image. That's what she wanted at the beginning. More than that, to enable constructive utilization of deepfakes, and also because she's also a music artist in her part-time, blend and explore melodies to compose music artificially.
May the cause be with you.